Easy BTech. I am Nawaz. I will be taking the structure analysis class. So in this video, we will be discussing about the analysis of propped cantilever. So this is the outline of this video. So we'll see the how to find out the reactions of propped cantilever for UDL in the sense uniformly distributed load, for point load and multiple point loads. Before discussing about this, let us recall the different formulas which you have derived in strength of materials for deflection and rotation. So this is a cantilever beam. If there is a point load at the end, then what will be the maximum displacement? So the maximum displacement will occur at this end, and it can be found out by this formula, PL cubed by 3A. Minus indicates in downward direction. And what will be the rotation? Rotation in a sense, here what will the rotation at this point is given by theta equal to minus PL square by 2PL. So this is also in downward direction. If we replace this point load with UDL, then the formula changes. The maximum deflection will occur at the end, and the formula is given as minus WL power 4 by 8EI. And similarly, the rotation will be given as minus WL cubed by 6EI. So these are the important formulas to be remembered while solving the propped cantilevers. Now, let us take an example. This is a propped cantilever. So we already know that in the propped cantilever, one end will be fixed, another end will be roller. So in the fixed, we have three reactions, that is AX, AY and AMA. And we have at the other end we have roller support, which is BY. Now we already know the number of reactions we are getting is 4 and number of equilibrium equations are 3. Now degree of static indeterminacy for this is 1. So let us take this example and we'll see how to find out the reactions. In this case, as already seen, the degree of static indeterminacy is 1. So here, degree of static indeterminacy is 1. Now, the first step which we need to do here is, this method is known as consistency deformation method. So in this consistent deformation method, what we'll do is, we'll replace this support and assume the load is acting here. And whatever the deflection is occurring here is due to this load. We are just replacing this support and we are assuming that a load is acting at that point and will equate the deformation occurring due to this load to the deformation occurring for the beam. So the first step will be, we have to find out what is the deflection is occurring due to this UDL. So we already have known that the deflection of cantilever beam using the for the uniformly distributed load is delta equal to WL for 8EI. Okay. Now this is the other case. Let me draw it. First, what we'll assume is this is a cantilever and a real is acting on of W per meter length, and whatever deflection we are occurring, so the deflection for this is delta equal to W L power 4 by 8EI. Right? Now we take this and equate it to the a cantilever beam to which a load of RB is acting. So there will be deflection because of this RB. That deflection, we know this is point load. The deflection due to the point load, the formula is WL cubed by 3A. Here instead of W, we'll write as RB L cubed by 3A. Okay. We'll equate this both, and from that can easily find out this reaction RB. That is the basic concept. So the first step here is to memorize this formula, deflection of cantilever using this UDL or whatever it is. Then the point. Now we are equating these two formula. This is due to UDL and this is due to the RB or point. After equating it, we'll take it this L cubed by 8A, L cubed by 3A here. So WL is outside, RB is outside. So L cubed will get cancelled, EA will get cancelled. Now I will send this 3 on the other side, so causing me RB 3 W8. So the reaction at the roller support is nothing but 3 WL by 3. Now, as the basic concept of the structural analysis is to find out the reactions. So we have found out this RB. We need to find out the reactions at horizontal direction, vertical direction, the moment. Since there is no horizontal force is acting and this end is fixed, the horizontal force will assume as 0. Now let us find out what is the reaction at RA. So RA is nothing but, if you consider this one, so RA plus RB will be equal to the load acting on this. Here the RA will be action. Here it is RB. So this is W into. Now from this can I write RA equal to WL minus R? This is what it has been written here. Now I am substituting the RB value here, solving it, I'll get 5 WL. Similarly, we need to find out the moment. So now to get the moment, we are taking moment with respect to A. So moment is nothing but load into the distance. So if we start taking the load moment from this point, we'll see we'll go from right to left. So the rightmost end we have RB at a distance of here. So this is my load, this is my distance, RB into L is my one moment acting, and when we come other side there is no forces acting. On the top there is a UDL acting. So UDL has a magnitude of W into L, that is W, it is acting throughout the air distance, and if we convert into equivalent point, this will act at a distance of L by 2. So WL is the magnitude and it will be acting at a distance of L by 2. So when we solve this one, we will get moment as W squared by 8 in negative direction, that is a hogging. So we assume this one as this is a hogging. Sagging in essence, the moment will come in clockwise direction. Okay. Now, so from this problem, we have found out by equating the deflection formula, that is RB equal to 3 to 8. Similarly, we have found out the RA reaction, that is 5W8, and the moment W squared 8. So these formulas are applicable whatever beam if it has the UDL through. This is the one formula problem. Let us see the another problem. So this is the problem. where we have got one point load acting on the, not at the exactly center, but at eccentricity. Okay, so the A distance is 2 meters, B distance is 3 meters. Now the load is acting here. That means we can get the, if we apply the formula of the deflection, that is delta PL cubed by 3EI, then this formula is applicable, gives me the deflection at this point below the load, not at the B point. But if you want to get the deflection, to find out the reaction, I need to get the deflection at B. For that, what we'll do is, we'll get the deflection, this deflection by applying this formula. Okay, and from this point, this deflection, we assume that this is constant. The deflection will be constant throughout the beam till the end of this beam, till here. So if whatever deflection we are getting here, this the same deflection will get at this end point B. After that, at the same point, we can also get the slope. Right? That slope formula we'll get it. The slope formula is given PA square by, is actually square, PA square by 2K. Okay. Now, using the properties of similar triangles, this distance is B, this is theta. So if we apply this tan theta formula, then tan theta equal to, if this is adjacent, this is opposite, so opposite to adjacent, I need to get this opposite value. So from here, opposite is nothing but adjacent, that is B into tan theta. Right. Here the theta we assume is small. If the theta is smaller, then tan theta will also become more small. It is will be much smaller. So we assume tan theta is equal to theta. Then this opposite side will be nothing but B into theta. Okay. Now this total deflection will become delta 1, that is the deflection due to the point load, and B theta 1 is nothing but the deflection at this point because of this load 30 kilonewton. After getting this deflection, we'll follow the same approach, equate it, get the reaction. Okay, so here the same formula have, right? That is PL cubed by 3A, PS square by A. The A is nothing here, A is nothing but this formula, A equal to 2 meters. And RB, the same thing which we used in the previous problem, that is PL cubed by 3. So we are substituting the values here. The delta 1, that is the reflection at the, this is my 30 kilonewton. So the deflection at this point is nothing but delta 1. So we will get this. After substituting, we are getting the 80 by EI. Similarly, we need to get the rotation here, theta 1. Theta 1 is nothing but this 32 square by 9. It is 60 by EI we will get here. Okay. Now the delta. So when we sum it up, this is B theta 1, this is delta 1. Delta 1 is 80 by EI and B theta 1 is 60 by E. Okay, now I need to get the delta here. So I need to, here it is not B theta 1, this is only theta 1. B in a sense we need to multiply by 3. When we add these two, that is what we are doing here, 80 by A, 3 is nothing but my B distance, 60 A nothing but theta 1. So substituting this, the data which we are getting is 260 by EA. Now we all know that we got the deflection due to the RB. It is RB into the overall distance, that is 5 meters. 2 plus 3 is 5 meters. 5 cubed by 3EI. So the compatible equation, we are equating these two. That's what we learned, the concept is, right? This deflection will equate it with the RB deflection. So when we equate it, we are getting, summarizing it, getting 6 kilonewton. So we have got the RB. We need to find out RA. The same approach. So this is my 30 kilonewton. This is my reaction. RB. RB is nothing but 6 point. I need to find RA. So RA is nothing but 30 minus 6.4. Similarly, we need to get the moment also. So the moment here is the same thing. This distance is 5. This distance is 2 meters. We need to find out the moment here. The moment, this moment. Moment is nothing but load into distance. We'll start from right to left. RB is acting at a distance of 5. This is RB into 5. Then 30 is acting at a distance of 2. That is 30 into 2. Now, here, since it is acting in anti-clockwise, whenever we are taking, remember that we need to follow this approach. You are standing at center here, okay, and you are trying to see if the moment is coming from in the anti-clockwise direction from right side. This is anti-clockwise direction. And if you are taking moment from the left side, if it is coming in clockwise direction, then you need to take this positive. Similarly, we have a moment which is getting in opposite direction. So you are standing here and you are trying to take moment. If the moment on the right side is having clockwise direction and on the left side it is anti-clockwise direction, then you need to take it negative side. The same thing here we are taking RB into 5. You are standing at this point, and if you see the RB is going in anti-clockwise direction. You see this? It is following this path. So it is positive. And if you see same thing, 30 kilonewton is acting downward direction. Downward in a sense, it is going in clockwise direction. Downwards is clockwise direction. So this is negative. Clockwise is negative. That's why here negative sign is getting. So calculating this, we are getting minus 28.8 kilonewton. Now let us see what are the, let us plot it, these reactions onto the exact. So we have 3 reactions. So MA we are getting minus 28.8 kilonewton meter. This is meter. Then RA is 23.76 kilonewton. RB is 6.2. So these are the reactions of this dropped cantilever. Let us see another example with multiple loads. So this is a problem. Here they have given the cantilever shown in figure has a rigid support 10 mm below. This is not meter, this is mm. Okay, 10 mm below the free end. So there is a fixed support, or fixed means rigid support, which is 10 mm below. The distance between these two, it is free cantilever, but the support is it is free to move only 10 mm downwards. After that, it has rigid support. And analyze the beam, and they have given EI is equal to 150,000 kilonewton meter square. Okay. Now, what should we do here? We are getting multiple loads. That is one case. Another case is we are getting we are allowing it to settle. This is a settlement problem. Call it like settle. We are allowing it to move 10 mm downward direction. So how to solve this problem? The same thing, what we need to do is we need to find out the deflection because of this 40 kilonewton, rotation because of this 40 kilonewton, then deflection because of this 60 kilonewton, and rotation because of this 60 kilonewton. The same thing after we need to find out what is the delta here. Because of these two loads, what is the deflection we are getting at this end B, and we'll equate it to the reaction, that is RB, causing deflection, and we'll get the RB. So we'll start it. So the deflection, this formula we have seen. So this is square PA cubed by 3A, PA square by 2A is the rotation one, and RBL cubed by 3A is the this thing, because of the deflection due to the RB. So now we'll substitute. First we'll take this 40 kilonewton. We'll start with this 40 kilonewton. We'll substitute this value. So here, due to deflection due to 40 kilonewton is 40 into 2 cube 3A, 40 into 8 by 3 into 150,000. This is EI value given. So when we substitute this value, we'll get 7.11 into 10 power 4. The rotation, the same thing. P L square by 2A. This is right. So substituting this value, 40 into 2 square is 4 by 2 into 150,000. This will give me 5.33 into 10. Then delta 60, that is deflection due to this 60 kilonewton. 60 into 4 cubed by 3 into 50,000 will get here 8.53 into 10 power minus 3. Same the rotation here. So let me plot it. This deflection I will get. This deflection is nothing, delta 40. From here, whatever rotation it is taking, it is theta 40. Now it will go till here, it will cause rotation till here. Okay. So this deflection we know, that is delta 60, and from here we will take theta 60, and this overall will be my delta. Okay. So we theta 60 also, after substituting these values in this formula, we'll get 3 into 10. Now let us see how to solve this. So we have deflection due to 40. Okay. Now this deflection here, if you see, second, we have a beam. Okay. The beam is undergoing some deformation. We are getting deflection. This gives me delta 40. Because of that, we are getting some rotation, theta 40. So we are getting this. Now at this point, because of 60, some displacement is taking place here. I don't know where exactly is displacement. If you compare this one, when delta 60 is more, right? Okay, so it will have some displacement like this here. So till here, this theta 60, and the rotation making here theta 60. So this both displacement will take place. So the rotations will match a single line like this, and the final end will be the summation of all these four. So this one, the same approach which we have given, that is delta 40 plus this distance here is 2 meters. Since we are taking here from the B end till 40, it is summation of 2 plus 2. So it is theta 40 into 4 plus the same deflection due to 60. Now 60 kilonewton is acting at 2 meter distance from support B. So it is theta 60. So this is what we have done here. This is my deflection due to 40. This is my rotation multiplied with the 4 distance. 40 is at the 4 meter from the support B. Then 8.53, that is nothing but deflection due to 60 here, this one. And 2 into 3.20 rotation into distance. Substituting that, get 0.0773 meters. Okay, now this is done. We have got the delta. As we can see here, we are allowing 10 mm, that is nothing but 0.01 meters. So this indicates that if we equate to this RB value, we'll get the reaction. But the reaction has some displacement, that of 10 mm. We are allowing it to settle 10 mm. We are not preventing 10 mm displacement. So we need to subtract this 10 mm from the obtained displacement because of the load 40 and 60. So what we are doing is we are subtracting 0.01 meter, that is 10 mm from this delta value. So when I subtract, we'll get delta 1, and when we equate this one to this RB into deflection of delta, we'll get RB 16.0. And remember that if they are allowing, there is a settlement in the sense we are allowing it displace till some certain limits, and till the displacement is taking place, there won't be any reaction, and we don't need to consider that reaction. The same thing here. Now, so the same thing, we need to find out the RA here. To find out the RA, we have cantilever, we have a reaction here. We found out RB, that is 16.0. And we need to find out this RA. We need to find out this. So RA is nothing but here we have 40 kilonewtons and 60 kilonewtons acting at distance of meter, right? So RA is nothing but 40 plus 60 minus 16.20, 83.80. Similarly, moment. To get the moment, 16.20 acting counterclockwise or anti-clockwise. That means positive, taking moment from A, and the total distance is 6 meters. Then 60 is acting at a distance of 4 meters in clockwise direction. That is why it is negative. 40 is also acting at a distance of meter. That is also negative. The overall solving this will get is minus 2.8 kilometer. Plotting this here, we have 4 reactions here. Horizontal is 0. Mostly the horizontal will be 0 in beams until unless some displacement is allowed. Then the moment, this moment reaction is minus 3.2.8 km/meter. Then RA is reaction acting upwards, that is 83.80, and RB is 16.2. So these are the important problems on propped cantilever, and this is how you need to solve it. Hope it is clear. If you have any doubts, please leave your doubts in comments. Thank you.